All right, welcome back, everyone. Let's jump right into it. For today's explainer, we're actually going to act as master architects. But, instead of building skyscrapers out of steel and glass, we are going to build, name, and completely understand complex molecules, just in time for your big chemistry exam. Think of me as your friendly site foreman for the day, guiding you through the blueprints of coordination compounds. Honestly, these are some of the most beautiful and brilliantly colored structures in all of modern chemistry, and by the end of this review, you are going to have the exact tools you need to absolutely ace your test. So, here is our blueprint for today's review. We'll cover history and anatomy, ligands and 3D geometry, decoding names and isomers, quantum bonding and color, real-world vital coordination, and finally, a rapid exam review. Okay, Section 1, History and Molecular Anatomy. Let's start by looking back to 1898, where a brilliant chemist noticed something that normal bonding rules simply could not explain. The core concept here from Alfred Werner is absolutely fascinating. He was looking at empirical data from some pretty simple precipitation experiments. When he added silver nitrate to different cobalt-ammonia complexes, totally different amounts of silver chloride precipitated out. And he was left wondering, why? Well, Werner realized that metals don't just bond to balance their electrical charge, which is what he called the primary valence. They actually also bond to fill strict, non-ionizable spatial quotas around themselves, which he called the secondary valence. This was literally a massive breakthrough for chemistry. Now, to answer your exam questions effectively, we really must memorize this exact definition of a coordination entity. A coordination entity constitutes a central metal atom or ion bonded to a fixed number of ions or molecules within a non-dissociating sphere. Basically, it's a single locked-in unit that behaves as one giant molecule when you dissolve it in water.
Think of it kind of like a molecular fortress. You have your central iron hub, the Lewis acid or electron acceptor, sitting right in the middle. Then, the cyanide ligands form a locked perimeter safely inside the non-dissociating coordination sphere, which we mark by those square brackets. Now, pay attention here, because here is the first of 3 common mistakes students make on exams. Do not confuse the ions inside the brackets with the counter-ions outside the brackets. The potassium ions on the outside, they'll dissolve and just float away in water. But everything inside those brackets is a solid, unbreakable fortress.
Moving on to Section 2, Ligands and 3D Geometry. Now that we have our central metal hub, let's take a look at the different types of hooks that actually attach to it.
Notice how simple, unidentate hooks, like chloride or ammonia, grab the metal at just a single point. But then you have these complex didentate or polydentate claws, like EDTA, that grab the metal at multiple points, creating incredibly stable ring-locked structures. And these hooks directly dictate the beautiful 3D geometries you're going to see on your test. Need a quick exam mnemonic for this? Just remember, 6 builds a box, 4 forms a pyramid door or flat floor. 6 connections give you the 8-faced octahedral shape. 4 connections give you either the pyramid-like tetrahedral shape or a flat square planar shape.
Section 3, Decoding Names and Isomers. With our 3D structure fully assembled, we need to learn the systematic language used to name our new creation.
Just follow this exact IUPAC nomenclature engine like it's a math formula, and you will perfectly decode any complex name on your exam. Step 1. The cation always comes before the anion. Step 2. Sort the ligands alphabetically and add prefixes like di or tri. Step 3. Name the metal. And Step 4. Calculate its oxidation state using Roman numerals. Now this brings us to common exam mistake number 2. Students almost always forget to alphabetize the ligands. Always sort them by their alphabetical name, like putting amine before chlorido, and completely ignore any of those prefixes when you're alphabetizing.
But beware of structural isomers on the test. These are tricky scenarios where the exact same building blocks are just anchored or arranged differently. You have linkage isomerism, where a ligand attaches via a completely different atom, ionization isomerism, where an inner ligand swaps places with an outer counterion, and so on. They have the exact same chemical formula, but entirely different physical properties.
You also really need to spot stereoisomerism. And here is common exam mistake number 3. Confusing geometrical and optical isomers. Geometrical isomers are all about whether identical ligands are adjacent to each other at 90 degrees, that's a cis isomer, or exactly opposite each other at 180 degrees, that's a trans isomer. Optical isomers, on the other hand, are chiral. That means their handedness is locked. The whole molecule forms a non-superimposable mirror image, kind of like your left and right hands, that uniquely rotates polarized light.
Pretty wild, right?
All right, Section 4, Quantum Bonding and Color. It's time to upgrade from macroscopic shapes to quantum mechanics to figure out why these compounds are magnetic and so brilliantly colored.
The science evolved dramatically over time here. We stepped from Werner's basic spatial mapping in 1898 up to valence bond theory to explain magnetism in the mid-20th century, and finally all the way up to advanced quantum models with crystal field theory in the modern era.
So, the absolutely crucial point here is understanding the difference between these two major theories. If you get a comparison question on the test, just remember that valence bond theory, or VBT, explains geometry and magnetic signatures through orbital hybridization. Crystal field theory, or CFT, relies on electrostatic point charges to unlock precise energy gaps, and therefore explains the origin of those complex colors.
Let's look closer at VBT. Under valence bond theory, the specific mathematical choice between using inner 3D orbitals or outer 4D orbitals directly determines your complex's magnetic signature. If the electrons are forced to pair up, the complex is diamagnetic. But if electrons remain unpaired, the complex is highly paramagnetic and will actually be attracted to a magnetic field.
And under CFT, we finally get to explain color. The complex absorbs specific photon energy to fuel a quantum jump for an electron, which then transmits the exact complementary color straight across the color wheel directly to our eyes. Hey, remember that simple classroom experiment where we added ammonia to a pale blue solution of copper sulfate? Almost instantly, bam, it turned a deep, brilliant violet blue. That is crystal field theory in action. The new ammonia ligands change the energy gap, absorbing different wavelengths of light and transmitting that gorgeous deep violet to our eyes.
Section 5, Real-World Vital Coordination. So, at this point you might be asking, why does all this molecular architecture actually matter to us in the real world? Well, it matters because of incredible mechanisms like synergic bonding. Take the metal carbonyl engine, for example. The ligand donates electrons into the metal, but then the metal pushes electrons right back into the ligand's empty orbitals. It's this awesome self-strengthening loop of electron donation and back donation that locks these architectures perfectly in place for heavy-duty industrial use.
And finally, Section 6, Rapid Exam Review. Okay, students, take a deep breath with me. Let's bring all of these concepts together into a rapid-fire summary for your final exam review.
I want you to take a mental screenshot of this table right here. Knowing these three foundational spatial architectures and their coordination numbers is guaranteed easy points on test day. Coordination number 6, it's octahedral. Coordination number 4, you just check the hybridization to see if it's tetrahedral or square planar.
And remember, this table of vital real-world impacts too. If you get an essay question, this right here is your secret weapon, proving that almost everything relies on coordination chemistry. From the iron hub in the hemoglobin carrying oxygen in your blood, to the cobalt inside vitamin B12, all the way out to industrial catalysts that manufacture our modern plastics and medicines. It's literally everywhere. To wrap all this up, a true master architect understands that the coordination entity is the ultimate intersection of science. It connects the systematic language of IUPAC naming, the 3D architecture of polyhedra, the advanced quantum mechanics of magnetism and color, and those profound real-world biological and industrial impacts we just talked about. It all builds perfectly upon itself.
So, now that you have the complete blueprint to ace this test, the real question is this. If coordination complexes are the engineered blueprints driving our biological existence and our industrial progress, what incredible, colorful, world-changing structures will you design next once you master this chemistry? Good luck on your exams, everyone, and keep building.